Thanks, Kelly. Hi, everyone. Thanks a lot for joining us today. In this session, we'll be talking about how at Pinterest we improved analytical productivity, specifically with Apache Iceberg. So let's get started. Let's talk about the first and the most important thing, which is about us. So I'm Ashish Singh. I work at Pinterest as a software engineer. I tech lead the big data query platform team here at Pinterest, which works on things like Presto, Spark SQL, file formats like Parquet, table formats like Iceberg. There's a bunch more interesting things, but these ones are the most related to this session. E, do you want to introduce yourself?
Yeah, so my name is E. I work under Ashish in the big data query platform team.
Thank you, E. Let's continue. So we're talking about data, and to win the credibility, we have to talk about the scale first. So here it is. At Pinterest, our business scale is around over 500 million monthly active users. We have multi-billion pins that are saved weekly, tens of billions of boards. And more interestingly, when it comes to data scale, we have around exabyte of data on AWS S3, 400,000 plus Hive tables, and we have all of our services and data in cloud. We typically use AWS. Okay, so in this session, we'll be talking a lot about analytical productivity. So just to be sure that we are on the same page about what this means, it's very simple. It's how quickly can an analysis be performed. But let's dissect this into particular stages of an analysis cycle, which, as per us, is identifying data sets. So given a problem statement, we first need to figure out, okay, which data sets has the relevant information that we need to process. And depending on like how many tables you have, like for Pinterest, we at least had over 400,000 tables. This is like finding a needle in the haystack problem. Once you have identified the data sets, then you perform a bunch of computations on it. Like that, this is where you write queries. You go through it like in several iterations. You use like build charts to look at trends, do a bunch of analysis. And once you have found what you are looking for, you essentially power the business decision based on that. You share the results with different stakeholders. So this is what the analytical productivity cycle is typically, at least at Pinterest, and very certain targets, other places pretty similar too. And we'll be talking about these specific stages and then how we made it easier at Pinterest and how Iceberg contributed to it. But before we do all that, let's just look at where is Iceberg adoption at Pinterest. So the table format evaluation at Pinterest over the period of time has went through various phases, but then until 2019, like many other industries, the Hive table format was a de facto format at Pinterest. Around 2020, we started running into various issues that the alternate table formats like Hoodie, Delta, Iceberg were trying to solve. And then we started evaluating like different formats, and then we finally made a decision to go out with Iceberg, and then we started building it out at Pinterest, which means like adopting it, getting approval from stakeholders, integrating it with various systems. But by end of 2022, we were running Iceberg in production. In 2023 is when we hit our first major milestone of moving all of our data deletion use cases to Iceberg. That was a big achievement. It enabled us to sunset a lot of legacy systems and processes we had to achieve similar data deletion use cases, which were much more expensive and were hitting like scalability limits. And then we continue to ramp up the usage of Iceberg. Two use cases that are becoming very popular with Iceberg at Pinterest is the machine learning data sets and the BI use cases. So with that, let's go back to the problem that we were talking about analytical productivity. So the first stage is identifying data sets. So here, we can think about this problem from two different personas, like data consumers and data producers, right? So data consumers, which is where most of the analysts assumes the role as, the questions they usually ask is like, how can I find the table for my analysis? Is the table I'm looking at, is that reliable to use in production? Are there better alternatives I can use? And similarly, the data producers, when they're producing data or like creating tables, they think about questions like, oh, where should I document my table? What kind of information should I provide? How can I enable more people to discover my table? And to help address these questions at Pinterest, we launched something called Pinterest Data Catalog. We just call it PinCat. And this is essentially a service that is based off open source data hub that we took. Of course, we made a lot of changes, integrated with a lot of systems at Pinterest. And this today has already become a central place for cataloging based data sets at Pinterest. It provides an easy UI for people, different data set owners, to go in and update information like description, the ownership, retention, and a bunch of other things about the data sets on the UI. We have a lot of different systems that allow end users to interact with tables, like querying the tables, adding descriptions and all that. So we provide an API layer for all of these systems to connect to the central data catalog. And on top of that, we allow various teams to add additional metadata on these data sets. For example, say a privacy team comes in, and they have a use case where they want to tag all the tables that have like user birthday for audits. And what they can do is like they can just programmatically query like which all tables have birthday column in it, and then like tag all the tables. And then the team that's performing auditing can query like all the tables that have birthday tags, and then perform audit on them. So this is one of the clients, or one of the pages of one of the clients where, and this is from Querybook, which is another open source querying client or tool open source by Pinterest. So as an analyst, to identify data set, they usually go to a client like this, in this case, Querybook. They search the tables by the keywords that that they think they are associated with the problem they're solving, and then they get a bunch of results, right? And then usually it's a long list, but then like here, based on the keywords, we are searching through the table names, the table description, tags. We have something called data elements, everything, and then we generate a big list of tables. Then the user usually, after looking at this long list, the user is usually thinking, okay, which of these tables is the most trustworthy, right? To help answer that, we introduced something called table tiering. So what we did was that, like, among all the tables we have at Pinterest, right, we thought that like it's going to be hard for us to improve the quality and documentation on all the tables. So what we can do is break them into different tiers, and then only focus on certain the high tier tables and improve their usability. So in our case, like, we have 3 tiers. Almost all the tables are in tier 3. So these are the tables which we don't care as much about. We don't care about their quality. We let users decide if they are really sure about using a table from tier 3, then they can. But we try to not show them on like various surfaces like the search surfaces. Then in tier two, we have most of our production grade data sets, which are discoverable in search, but it doesn't have any of the reliability guarantees or the various other value-added services that we provide specifically for tier one. Tier one is where we promote those tables on the search surfaces. It meets the highest standards in terms of freshness, quality, and is also reviewed by domain experts. On top of that, we also provide various value-added services like automated validation, user statistics, and more. This tier one classification, oh, by the way, like when we say tier one, we try to keep it like in a couple of hundreds, only a couple of hundreds of tables in there. Tier two, couple of thousands. Tier three, everything else. So this categorization of tier one not only helps our consumers, but then also helps the platform teams so that because now we can focus all of our efforts on just a specific set of tables. We can look at how these tables are used, like what columns are accessed, and the query patterns, and essentially build our roadmap so that like we can make the tier one really performant and efficient. And at Printest, the way we are doing this is by moving these tier one tables to Iceberg so that they get the latest and greatest, and then we focus on only on Iceberg and on tier one tables. Okay, then the usual life cycle for a table creation is that like a user comes in, they create the table, it's in tier three, and only when they meet certain criteria, the table automatically gets promoted to tier two. And if they meet certain criteria, and then like it's reviewed and approved by the data stewards or data governance committee, then it gets to a tier one status. And once it gets to the tier one status, all the value added services kicks in. And a bunch of those value added services are actually powered by Iceberg. One of those is table statistics. So a lot of time, I'm sure like you all have also run into this, but what we try to do is like, okay, we have to use a table. We first try to figure out, okay, like we ask the data on the data, which is essentially like, oh, is the count of the table stable throughout past few months? What is the standard deviation? Like how many rows do we have in this table? Things like that, right? To understand the data that's in the table. And this is something that we can help answer just by looking at statistics of the table. And so that the users don't have to run a query just to find this very basic information. So we capture all the statistics, and this is where Iceberg plays a big role as well, because Iceberg, you all know, we capture like various statistics at the table level, and then also at the snapshot level, and that is something we can utilize to even look at the history of like how the number of rows has evolved, like various statistics has evolved for a given table. This helps users or the consumers look at and see, I'm seeing a huge deviation for this column and my downstream checks are failing. So all that like users can just understand the changes just by looking at the history and without running a single query. Then so right now where we are at is in the identifying data set problem of the analyst productivity. We are able to list the tables by search the tables by the keywords. Just by looking at the table tier, we can figure out whether the table is reliable or not. Look at the statistics to understand the data aspects of the table itself. But then like this got us to thinking, okay, so we are trying to make our users not use majority of the tables. Why are we even keeping those tables? So this is where the garbage collection comes in, and the associated table maintenance part of the Iceberg. At Printers, I mentioned a few times already, the number of tables has grown significantly. Like we at end of 2023, we are at 460,000 tables. And we asked ourselves like why the number of tables are growing. So there were three categories that we could think of. One is there wasn't any incentive to delete tables, the lack of ownership information, and lack of mechanism to delete save tables reliably. We address those concerns by changing the user behavior, and we made that the default behavior would be the table will be deleted after X days. And instead of like asking the users to delete it, platform itself will delete the tables. And then we tied in the adding the ownership information as part of like the table tier promotion mechanism, and to delete the tables reliably, and then be able to revert the deletion. We added soft deletion mechanisms where we first soft delete, and if the user wants to revert back the deletion, they can request the deletion reversal. So this built a very confident mechanism that we can use to delete, even in the cases where we are not sure if we can delete the data or not. This is a very high level garbage collection architecture, but essentially it goes through, it provides the soft deletion, hard deletion, and the revert capabilities. And this is where we also plug in the Iceberg procedures like orphan file cleanup, expire snapshot, and in future we want to expand that to also do things like data compaction. So with all these changes, we were able to actually make a big dent in the number of tables. So last year, end of last year, we were around 460,000 tables, and now we are around like 300,000 tables. And we have a plan to get to 100,000 tables by end of the year. Pretty challenging, but I think we are making good progress in that direction. All right, with that, I'll hand it over to E to talk about the velocity aspect of the computations.
Thanks, Ashish. So I will continue to talk about the query velocity efforts in Pinterest and how Iceberg play a role in it. So let me start by showing basically how our platform looks like over the years. So we are previously mostly a Hadoop shop that runs queries and workloads on Hive and Presto and the Spark. In 2020, we started to migrate away from Hive queries, and our query engine consolidates into Presto and Spark SQL. And we support machine learning use case in PySpark and streaming in both Spark Streaming and Flink. Currently, we started to onboard our data set into Iceberg's tables and start to run our Spark jobs on EKS. And we are consolidating our programmatic job into Spark, streaming job into Flink, and evaluating adoption of Gluten and Velox in Spark and Spark SQL jobs. We are also looking forward to move our CDC ingestion job in Iceberg. So the first thing we did to improve our dev velocity is basically through collocated join. So what is a collocated join? We ask our user. So basically, we ask our user to bucket their Iceberg tables by common join columns and keep the bucket size between 1 to 5 gigabytes. Basically, by doing that, this allows the query engine actually to optimize the joins into collocated join to avoid basically shuffle cost by basically co-locating buckets that contains same value from different table on the same physical nodes. As a result, this allows a faster query or allows joining bigger tables possible, which was previously prohibited by the shuffling cost of really large table we have. We actually have sometimes we have like hundreds of terabytes data needs to be shuffled. So basically, to make that happen, we leveraged the open source support in Spark SQL, and we added a trainer support for Iceberg collocated join. we decided not to go to support non-bucket columns as we found it out that it often causes bucket join condition to break easily. So so how did we implemented the bucket join, collocated join? So basically for table one and table two joined together by column A and B, we bucket both table by the join key, which is A and B. The number of buckets does not have to be the same as long as it is divisible by each other. So for each bucket column, we pick the smallest bucket number as a compatible bucketing number. And when we calculate the split assignment from both join side, basically what we do is we mod the bucket ID of that split by the compatible bucket number, join the multiple columns together as a hash, and basically mod by the total number of buckets to get basically ID that map to the assigned node ID to that bucket ID. So that way, basically, so the split reading same values for the bucket columns can be collocated into the same machine, basically. And basically, then we get rid of the whole shuffling process, and basically, the query runs much faster. The second thing we did for query velocity is table sampling. So actually, so basically, basically using table sampling, we basically read only 1% of data or whatever the user chose, to basically instead of reading the full data set for query. So for Hive table, what we did is basically we write another copy of the table that has only sample data, like for example, like 1% of the user IDs. And in our queryable UI, we rewrite this query to read from the sample table instead of production table when user chose to. For Iceberg, actually, we are able to leverage the fact that we can have a bucket table in Iceberg, and we can leverage the query engine to do sampling push down into to Iceberg. So by carefully selecting proper bucket columns, such as, like, for example, user ID, and we were able to ensure the sample data actually is joinable between tables and has statistically close enough result against the production table. So this slide shows actually how our UI looks like for enabling sampling for user query. So when sampling is selected by the user, we basically the query will be rewrite underlyingly and sent to the query engine, and we can clearly see a significant difference in the query runtime, which this basically enables our user to do a quick query prototyping, and that they iterate quickly and then once they finalize and query, they can continue to write a production query without the sampling. So basically, the result of sample data actually is, when upscaled, actually is pretty good, close to the full data set if we chose the sample column properly. So actually, for less complex queries, for example, we see less than 0.5 deviation from production queries when we tested the. So how do we sample the data? So basically, so generally we basically select a few dimensions that we know that this data of that table can be evenly distributed, and then we bucket the table by it. If we don't have enough bucket to cover sampling, we generally further divide files by the hash of path. So for example, if we want like only want 1% of sampling, we have 10 bucket of A, column A, and 5 bucket of column B. We basically select one bucket out of the total 50 bucket, and then we divide files under the select bucket into two portions and select only one portion out of it. If you have 10 bucket of A and 100 bucket of B, basically we select 10 buckets out of 100 bucket for column B, basically. Uh, so the third thing actually we did is for query velocity is gluten and veloc in Spark SQL. So basically, we started evaluating native execution engine in Spark a few years ago. We noticed that most improvement in Spark after 2.0 was achieved not by improving operator performance, but by better planning. But actually, when we looked into it, then we realized that there is actually a bit of performance we can squeeze from these operators, especially scan, filter, and projection. So basically, using native code and hardware vectorization, we often can see 2 to 3 times speed up in these operations. And so basically, we partnered with Intel actually on adoption of gluten and veloc in Pinterest. So basically, we worked with them on a lot of missing features, bug fixes, and Iceberg integrations. So currently, we enabled it for interactive queries for user to try out, and we are starting to see an increase in of adoption. So how we route the query to Veloc enables Spark SQL is that basically when users submit a query from their query authoring UI, like for example Querybook and Jupyter, so it will submit the query to Libby service, where we will basically run a explain query in background to check if this query can be fully converted to a gluten veloc-based plan. If yes, we run the query in gluten veloc enabled Spark session. If not, we basically just fall back to vanilla Spark session. So we basically tested and validated over 200 Spark SQL jobs on Veloc. On average, we have seen about 60% improvement on vanilla Spark and 60% reduction in memory utilization. And 86% of job tested, we saw improvement on Veloc, while only 8% of jobs we saw performance degradation greater than 50%. And then I want to take this opportunity to actually thank for our partner teams, especially II and business intelligence and the data warehouse team at Pinterest, because a lot of the efforts we mentioned before actually couldn't happen without their help. And then thank you, and we are ready for some questions.
Hi, awesome. So thank you, Ashish and Yi. I would now like to open it up for questions from our audience. You can type them in the Q&A tab to the right or ask your questions on camera, but we do have a few that came through. So the first one is, what workloads did you decide to run on Spark versus Trino versus Ray, and why?
Maybe I can take that one, and then feel free to add. So when it comes to like Spark versus Trino, it's mostly a question of like if the user needs fault tolerance. We on Trino we don't provide any fault tolerance. Like if the task fails, the whole query fails, and then the user is expected to retry. For that reason, we only allow queries up to 1 hour of query runtime, because we don't think it's the best user experience or the resource efficiency if we allow a query to run for like 10 hours and then let them fail. So that's why like we have a query runtime limit on Trino. So if our users have a small query and then they care about latency, then they go with Trino. If they want like fault tolerance and then they want to run like super large queries, they go with Spark. When it comes to Ray, we typically use that for the last mile processing. So huge ETLs and compute still happen on Spark, Trino, and then for the machine learning specific last mile processing, the users then interact with or use Ray.
Okay, great. Thank you. And then the next question is, you mentioned evaluating other table formats in 2020. Have you done a more up-to-date table format evaluation? And if yes, how does it compare? Or any insights on your choices if this applies?
Yeah, I think let me take that one as well. So in 2020, it has been like 4 years back. A lot must have changed, but at that point, we did a thorough evaluation based on the Pinterest data sets and the Pinterest use cases. And based on the requirements we had at Pinterest, we saw that Iceberg was best suited for those use cases. And yeah, we went ahead with Iceberg. I don't think like even if I give you the exact numbers on the performance difference or exact reasons, I don't think they will be relevant today. So for that matter, I think I just want to say in 2020, it was Iceberg was best suited for our business use cases.
Yeah, great. Do you have a concrete example of where creating a bucket table would make sense versus when it would not?
That I can probably take it. So I think example of definitely not make sense is if the data has skill, is definitely not going to make things better. And we are see cases basically when like for example joining two big table actually bucketing actually would help if we bucket properly. So basically, what we usually see is when there is basically if we have to do shuffle versus we can basically read the data and join locally, that the performance gain is actually quite significant. And actually, for like even like for small tables, actually bucketing actually would also help too, because actually that basically that shuffling overhead sometimes could become really critical too in those performance. But usually when you have a lot of join queries actually play a really important factor on the query performance basically.
Great. The questions are coming in. So is the table catalog integrated with access control? How is it managed with the 3 tiers?
I can take that. So table catalog right now it's just Hive catalog. Is it integrated with access control? We don't do access control at the table metadata level. We do access control at the data access level. So we rely on S3's access control. And the way it's done, it's a little more, I think, larger discussion. But we have a mechanism where, based on the user who is running the query, we get like different STS tokens for our S3 access and use that to access the S3 objects. But yeah, if there's any follow-up discussion needed, our contact details are on the slide. Happy to discuss more. How is that integrated into 3 tiers? The table tiers have nothing to do with access control as of now, and I don't think that it has to. There's no plan to bind the access control with the table tiering.
Can you describe more on the future work regarding Flink CDC ingestion?
Do you want to take that?
Yes, actually, we are still on the POC phase on that. Actually, we have seen some good result on that, but I think mostly we just going to productionize in the coming probably in by end of 2024.
Cool. Okay. Next one. Any guidelines you have identifying on a good GB partition count number amount? Said differently, is there any tuning you apply when choosing your partitioning bucket value?
Oh, this is a growing pain point as as we push more use cases on bucketed tables. So this is definitely more of an uh, like a trade-off that you need to consider. So the things that we ask our users to consider is when you're doing bucket join, right? Like if your bucket sizes are very large, then you are at the risk of running out of memory, right? And in case of Trino, you won't be even able to do the joins, right? Then if the bucket size is too small, then you have too many buckets, and then that really will affect in terms of like the compression ratio that you see, and also it's like it will just launch like too many executors for if you're just joining it with different tables. Typically, we say that like try to keep your bucket size big enough so that it has more than at least 1 gig of data, and it's smaller than it can fit in one executor memory. The recommendation for the executor memory we have is like by default we give 4 gigs of executor memory, but then like we allow users to go beyond, but then we definitely ask them to keep it below 32 gigs. So anything between 4 gigs, any bucket size that can fit between 4 gigs of executor memory and maybe 16, 20 gigs of executor memory is reasonable. The moment you go below or above that, things can get tricky. And then we work very closely with the users to figure out the exact details.
Great. Okay. There's still, we only have 4 more minutes, so I'm going to read a few more. And then if you guys hadn't seen, the poll is live, so please do rate the session. So now we'll go to, for the bucket join, did you commit back to Trino, or was that an internal fork?
Right now is an internal fork, but we are eager to contribute that back to the Trino branch. Yes.
Great. How do you balance between the bucket number and the small files?
I think we already went over this, so it's a yeah, you have the trade-off. So I think it's kind of answered.
And then this is going back to that original question, a bit more detail on Ray's solution. Do you use Iceberg together with Ray?
We do use Pi Iceberg together with Ray. So yeah, we still use Pi Iceberg to get the files. Actually, Ray use cases are the only use cases where we allow users to list the actual files from Iceberg and operate on them. And we also allow them to specifically add files. All other places we don't allow users to do that. But for Ray, yes, they use Iceberg to list the files, list the partitions, and then actually the Pinterest team is actually doing bucket join even on Ray using Iceberg. So yeah, to answer your question, yes, Ray is used with Iceberg.
Awesome. Okay, well, that is the end of our session. Thank you guys so much again, and enjoy everybody the rest of the conference.